In question 1, we're asked to find the domain of our function. So this function has a denominator, and in the denominator there's a square root. Well, the denominator can't be equal to 0, and whatever's underneath the square root has to be greater than or equal to 0. So combined with the fact that it can't be equal to 0, it has to be strictly greater than 0. So we have what's under the square root, 3 minus x, must be strictly greater than 0. Adding x to both sides, we have 3 greater than x or x less than 3. So that's our domain. In number 2, we want to see if f of x is odd, even, or neither. All right, so we look at f of minus x, and if f of minus x is equal to f of x, that means even, or if it's the negative of f of x, that means odd. Otherwise, it's neither. All right, so we start with this. Instead of x, I'll just put parentheses, and I'm going to fill in with minus x. Okay, now let's simplify that. When we cube this out, we get a minus coming out in front. And here we have minus minus, that's plus 3x. And under the square root, we have x squared. So when we square that out, under the square root, we have a minus x squared. Square it out, and that's x squared. Okay. All right, so you see we can factor out a minus 1 from the numerator. All right, so we can put like a minus in front of the whole expression, and we have in the numerator 2x cubed minus 3x. Which is equal to minus f of x. Okay, so we got that f of minus x is equal to minus f of x. That means that our function is odd. All right, here again we want to know if our function is even, odd, neither, or both even and odd. Well, just about no functions at all can be both even and odd, unless it's the function f of x equals 0. Unless it's always 0, then it's both even and odd. But other than that, a function can't be both even and odd. So it's going to be either even, odd, or neither. So let's do that. Again, we have to see what f of minus x is equal to. So we're substituting minus x for x. Okay, so here, because of this even exponent, minus x to the fourth is the same as x to the fourth. And here also, because of the even exponent of 2, minus x squared, that's the same as x squared. So we see that f of minus x is exactly the same as f of x. So in number 3, our function is even. In number 4, we just want to evaluate this piecewise defined function. So first we'll start with f of minus 2. All right, if we substitute in f of minus 2, we have to use this top expression because minus 2 is less than 3. So we use the top expression. That's minus 4 plus 5, so that's 1. And now let's find f of 10. All right, use the bottom expression for that because 10 is greater than or equal to 3. So that would be 7 times 10 plus 2, or 72. And now we want to find f of 3. All right, so since 3 is in this interval, x greater than or equal to 3, we use the bottom expression again, 7 times 3 plus 2. So that's 21 plus 2, or 23. Our number 5, we want to find the limit, and if it doesn't exist, we want to explain why. Okay, so here we're taking the limit as x goes to 1 of f of x, where f of x is this piecewise defined function that splits at x equal 1. Alright, so because it splits at x equal 1, and we're taking the limit as x goes to 1, we have to first take the limit from the left and then from the right. From the left we use the top expression, because that's x less than 1, and from the right we use this bottom expression, because that's x greater than or equal to 1. So we're doing the limit as x goes to 1 first from the left of f of x, and we'll use the top expression and we'll substitute in 1. So that's 2 times 1 plus 5, or 7. Okay, now the limit as x goes to 1 from the right of f of x, use the bottom expression. Okay, so that's 1 plus 6, or 7. Alright, so since these are the same, or since these are equal, that implies that the limit as x goes to 1 in either direction is equal to 7. So the limit does exist and it's equal to 7. Okay, now we want to find the limit as x goes to 3. And again, we have a piecewise defined function that splits at 3. Alright, so again we take a left limit and a right limit because it's piecewise and because it splits at 3. So we have the limit as x goes to 3 from the left. Use the top line and just substitute in. So we have 6 plus 1, or 7. Alright, and now from the right, use the bottom line, and we have 3 plus 5. So that's 8. Now since these are different, okay, we have the limit as x goes to 3 from the left is not equal to the limit as x goes to 3 from the right, and that means the limit does not exist. This is one of the most common reasons for a limit not to exist, that the left limit doesn't equal the right limit. Alright, another place, or another reason why a limit might not exist is if it's infinite, or if as we approach whatever our number is, whatever c is, our function's going to infinity. That's another reason, another common reason. Okay. Alright, here we're doing the limit as x goes to 3 of f of x, where f of x is equal to the absolute value of x minus 3 over x minus 3. Alright, now this is this function containing absolute values can be written as a piecewise defined function without the absolute value. Alright, because the absolute value of x minus 3 is just equal to x minus 3 when x minus 3 is greater than or equal to 0, or when x is greater than or equal to 3. And the absolute value of x minus 3 is equal to minus x minus 3 when x minus 3 is negative or less than 0. Or that is when x is less than 3. Alright, so now if we open up absolute value of x minus 3 over x minus 3, that's equal to minus x minus 3 over x minus 3. Or minus 1 when x is less than 3. And it's equal to x minus 3 over x minus 3. Or it's equal to 1 when x is greater than 3. I left out the greater than or equal to because in this expression x can't be equal to 3 because then the denominator would be 0. So I left that out. So I just put an x less than 3 and x greater than 3. All right, so then rewriting this one more time, our function f of x is equal to absolute value of x minus 3 over x minus 3, which is equal to minus 1 when x is less than 3, and 1 when x is greater than 3. Okay. All right, now for the limit, we want to take the limit as x goes to 3. We'll do it in two stages, from the left and the right, because this function splits at 3. Okay, so from the left, we just have minus 1. And from the right, we have a function that's equal to 1. All right, and so these are not equal. So that implies that the limit as x goes to 3 of f of x does not exist. All right, let's look at number 8. All right, we have the limit. I'm going to rewrite this one. The limit as x goes to 8 of the square root of x plus 1 minus 3 over x minus 8. Now, notice that if we substitute in 8, obviously the denominator is 0 when x is equal to 8. And the numerator as well. We have 8 plus 1, that's the square root of 9, which is 3. So we end up with 3 minus 3, or 0, in the numerator. Okay? So when we substitute in 8, we get 0 over 0. So this type of limit is the type that I call a 0 over 0 limit. Okay? And one thing we could try is try reducing this. Try somehow to cancel out x minus 8 from the denominator and numerator. All right. When we have an expression with a radical plus a number or minus a number, we try multiplying top and bottom by the conjugate in order to manipulate the expression. So let's do that here. Okay, this is the conjugate. In other words, the same expression with a different sign in the middle. Right. So we're going to multiply numerator and denominator. Okay. Limit x goes to 8. Here, when we multiply these conjugates, we get, remember that the middle term drops out, so we just get x plus 1. That's for the root times the root, we just get x plus 1. And then the middle term is minus 3 times the square root plus 3 times the square root. That's 0. Now for last times last, we have minus 3 times 3, which is minus 9. All right. And over here in the denominator, we have x minus 8 Don't multiply this one through. Keep the x minus 8 outside. Notice what this is on top, x plus 1 minus 9, that's x minus 8. This is x minus 8, which cancels with this x minus 8. We can reduce this expression. Remember, we can do that when taking a limit. We can reduce and then take the limit. So that's what we did here. We reduced first and then take the limit. So now the reduced expression is 1 over square root x plus 1 plus 3. Now if we substitute in 8, we no longer get 0 in the numerator or denominator. Alright, so now we can go ahead and take the limit and substitute in 8. Alright, so that's equal to 1 over the square root of 9 plus 3. And this is square root of 9 is equal to 3. So that's 1/6. The limit is 1 over 6.